Welcome to a brief demonstration of Virtual Software Systems Extended Resilience Architecture called X-Ray. X-Ray protects mission-critical IoT systems by applying fault-tolerant principles to create new or modify existing applications that deliver new dimensions of resilience, reliability, availability, and safety. X-Ray enables continued operations despite hardware failures or software anomalies. X-Ray creates application replicas that compare each other's execution at the thread level, that identify the source of the fault by consensus, and take corrective action with a detailed log for analysis before harm occurs. As an architecture, X-Ray has advantages versus traditional fault-tolerant technologies because it applies to only the core of a system's functionality, the application. Its design provides hardware and software host independence, reduced execution overhead, and protection against software execution anomalies, such as Heisenbugs. This illustration of the demo shows how X-Ray creates process resilience using common IoT components. X-Ray application replicas are distributed across multiple hosts and connected to their associated temperature sensors to control a critical process in a chemical plant. Analogous control systems are used worldwide for many critical temperature-sensitive systems and processes, including chemical, mechanical, and power generation. In this manner, X-Ray applications help protect critical processes against failures caused by computers, sensors, networks, and software. As shown, the self-contained demo fits in a 12 by 20 inch case. It uses typical off-the-shelf hardware and software. Raspberry Pi computers with ARM processors running Linux operating systems with Python and C languages. Components used in millions of IoT control systems worldwide. Note that the X-Ray application replicas may also be implemented across a wide range of heterogeneous hardware and software platforms using virtual machines, containers, or bare metal, located in-house, in the cloud, or on the edge. The primary demo components include a heating element with temperature-regulating fans that represents the process or device being controlled or monitored, 3 independent process controllers, each consisting of a connected temperature sensor and a Raspberry Pi control processor running its respective X-Ray application replica. A small interactive screen that provides demo process control input and displays individual and average controller temperatures. Network connections, power control relays, and an automatic emergency cutoff. The display reports average and individual sensor temperatures from all X-Ray replicas every second on a wrapping graph across a 120-second timeline. Temperature ranges are displayed in various colors. Target temp is in green, under temp is in blue, and over temp is in red. Note that the graph dotted line in these images shows the initiation of the process and the temperature increase from the ambient under temp to the target temp. The status of each process control X-Ray replica is displayed on the sensor status bars at the bottom of the display. Green is for active sensors and yellow, as you'll see in the failure resilience demo, represents inactive offline sensors. Other process controls and status information outputs required for operating and controlling the demonstration, such as notices, logs, heater and fan controls, etc., are displayed on the right side of the screen. To demonstrate continued process control despite a hardware failure, a failure was introduced in the controller running replica number 3, as shown on this display screen video. Following a very brief interruption for analysis, all status bars turn yellow. The X-Ray replicas determine the source of the fault by X-Ray consensus management and remove the non-concurring replica number 3. Process control continues with the 2 remaining replicas number 1 and number 2, whose status bars remain green. To further demonstrate X-ray resiliency, A software anomaly has been introduced into replica number 1. Again, during a few seconds interruption, when all status bars turn yellow, X-ray removes the faulty replica number 1 and critical process control continues with only one replica number 2, represented by its green status bar. At this point, having successfully recovered from both a hardware failure and a software anomaly, this 3-replica X-ray process control system continues operation. Despite both failures, the demo shows how an X-ray application continues its mission-critical process functions. Lastly, note that up to 32 replicas are supported in the current implementation of the architecture. So if additional X-ray replicas are implemented, an X-ray system would tolerate even more hardware failures or software anomalies while it continues to maintain process control. In summary, X-ray enables IoT developers to create autonomous control systems to protect critical IoT processes against hardware failures and software anomalies that adapt to a wide range of hardware and software platforms and that can run on geographically distributed heterogeneous hardware and software platform configurations in data centers, in the cloud, on the edge, or in any combination thereof. Thank you for taking the time to view this demonstration of X-ray for resilient IoT process control. Let us know how we can help you adapt X-ray technology to meet your needs.